Okay, hello everyone. I'm Yan Song, a postdoc at King Abdullah University of Science and Technology, affiliated with the Spatial Temporal Statistics and Data Science Research Group. Today, I would like to introduce our R package ExaGeoStatCPP. Its development is led by our research scientist, Sami Abdullah. So here I just illustrate an application of ExaGeoStatCPP to show how to use this R package to efficiently simulate Gaussian random fields with, for example, the Matern covariance function. And I will also mention how the change of the parameters in Matern can influence the patterns of the simulated Gaussian random fields. Okay, so here we assume that this capital ZS represent a Gaussian random field at location S. Then the Matern covariance function models the covariance function between capital Z of Si and capital Z of Sj in the following parametric form. So here we can see this covariance function relies on the distance between these two locations and four parameters, the sigma square, the partial seal sigma square, this range parameter beta, the smoothness parameter nu, and this nugget tau square. So we will begin by setting up the ExaGeoStatCPP with GPU. So here we just need to run this code, which will take us about 15 minutes. And then we can use it to simulate Gaussian random fields. Yes, we need to load the necessary R package first, for example, so like here. And then we also need the fields R package to help us to visualize the data, the simulated data. Okay. So here we will use the simulate data function in ExaGeoStatCPP to simulate our Gaussian random field. So here we assume we want a 2D Gaussian random field with the Matern covariance function with parameters set in this way. Okay, so we need several variables to be set for our simulate data function. For example, the n cores means the number of CPU cores, the n GPUs means the number of GPUs, the DTS, LTS means the tile size. The computation we can choose approximate or exact. The PQ are parameters in shared memory system. The closer these two values, the better the performance we will have. And we also need to set variables for the specific simulation problem. For example, the dimension of the locations. So here, for example, we choose 2D and the problem size or how we want to simulate the Gaussian random field on how many locations. So here we choose 10,000. And here the kernel means the names of the covariance functions. So here for the Matern, we will use this univariate Matern stationary. And we also need the initial theta, which means the parameters in covariance functions. Remember, we set this vector to this initial theta. And we also need this the path to save the simulated data. Okay, so now we use this simulate data function with all the parameters we set before to simulate the Gaussian random field of a specific problem. And we also record the simulation time. We visualize the data here. And so for ExaGeoStatCPP, this simulation takes about 23 seconds. So we compare this ExaGeoStatCPP with the existing R package GeoR. So we can also simulate a Gaussian random field of the same size using this grf function in GeoR. And here we load this R package. We set the specific problem, and we use GRF to simulate this Gaussian random field. We visualize the data, and here we see this is the simulations generated by this GOR, and it takes about 54 seconds, which is almost double time of the ExaGeoStatCPP. So finally, we also try to change the smoothness parameter nu and range parameter beta in the Matern covariance function to see how they can influence the patterns of the simulated Gaussian random field. So we fix the sigma square and tau square, and we select the values of nu from this set and the values of beta from this set. And we visualize the resulting simulated Gaussian random fields. So here, for example, we have fixed nu equals 0.5, and we increase the value of beta, and we can see the larger the value of beta, the stronger the correlation in the simulations. And we also increase the number of the value of nu from 0.5 to 1.5. And we can see the larger the value of nu, the smoother the patterns can be. Okay, that's all. Thank you.